Hello, everyone. I want to talk about VSEPR theory. It's a long conversation, so I'll try to wrap this up pretty quickly here. As far as VSEPR theory goes, we're talking about the valence shell electrons that don't want to be around each other. That's what VSEPR is, valence shell electron pair repulsion. So the electrons, again, the valence electrons, those outermost electrons, really don't want to be around each other, so they're going to orientate themselves as far away from each other as possible, which is what that second phrase means, okay? Now, whenever we talk about this, there's a couple ways we can consider this. Everything is based off of what's called electron domain geometry, okay, which is where we're going to consider all the electrons that are locked in bonds and all the electrons locked in, hold on, let me do this right here, all the electrons locked in bonds and in lone pairs, okay? So we have shapes, and the general shapes are linear, where there are two things bonded. We have trigonal planar, where we have three things bonded to a central atom. We have tetrahedral, which are four things bonded to a central atom. We have, and you get the idea, then we have trigonal bipyramidal, which is five things. And of course, six things, which is something called octahedral. Okay, 3, 4, 5, 6. Okay, so that's the electron domain geometry. Okay, now sometimes we have lone pairs in here, which changes the shape but doesn't change the electron domain geometry. In other words, there's still 1, 2, 3, 4 things around the central atom. So as I go through this, I will talk about how the EDG, the electron domain geometry, the regions of electron density, does not change as long as we're within a shape. So if you take a look at this thing here, this is a bent shape. Okay, you don't see lone pairs when we talk about the VSEPR theory or molecular geometry. So it is a bent shape. But how many regions of electron density are there? There are 4 regions of electron density. In other words, 4 electron domains. We have 1, 2, 3, and 4. So this is really based off of the tetrahedral shape. Okay, but its true shape is that it's bent. Okay, it's really based off of the tetrahedron. So as we move through here, we'll talk about that. What I like to do is separate these things into 2 categories: shapes with no lone pairs around the central atom and shapes with lone pairs around the central atom. Okay, let's talk about shapes with no lone pairs. Okay, so this is truly the EDG, the electron domain geometry. So when we talk about that, we have 2 electron domains, one here and one here. Okay, so we have regions of electrons here, and the same thing here and here. But notice, I have beryllium. This is an electron deficient molecule, atom, or forms electron deficient molecules. In other words, non-octets. Here is carbon dioxide, which forms a octet all around. But it's linear, okay, because there's no electron pairs around the central atom. So this is truly linear because there's no, again, lone pairs here around the central atom. Those don't exist, okay, so probably shouldn't even draw them in. The second shape that is also has no lone pairs around the central atom is something called the trigonal planar molecule. This sits in the plane of the board or plane of your paper. There's 120 degrees here. You can get this several different ways. Boron is a typical example of something that would form an electron deficient model. Another example is something like CH2O. Okay. Again, 3 regions of electron density. So this is truly this is truly a trigonal planar molecule, okay? Another one is called the tetrahedron, okay? The tetrahedral shape looks like this. It's got 4 things attached to a central atom. There's 109.5, and this is the most common and stable geometry that we know of. This is actually diamond right here. This is diamond. This could be CH4. It could be CF4. It could be CBr4. You get the idea? Okay, there's a couple different ways to do it. Of course, Si, F4, you get the idea. So carbon and sulfur, carbon and silicon are both in the same group. Okay. Anyway, the next shape that has no lone pairs, again following the EDG pattern, is called the trigonal bipyramidal molecule. We have a central atom, which is A, and then we have 5 things bonded to that central atom, which is B, 2, 3, 4, 5. So that's the AB5 pattern that's here. This one's a little complex because this is 90 degrees, but this here, here, and here is each 120. So this one actually has some choices here on where it's going to put those electrons. Trigonal bipyramidal is extended. Actually, the one side I don't have, I'm really kind of ashamed about this, is the octahedral, which is an AB6 pattern, and it's 90 degrees all around. So now let's switch our categories to shapes with lone pairs around the central atom. So you have to understand, when I talk about trigonal pyramidal, this is actually a tetrahedral shape. The EDG is tetrahedral. So it has actually 4 things around it, but all you see are 3 things pointing down, giving us a trigonal pyramidal shape. Bent, same thing. We've already discussed this one. It's also the EDG, or the electron domain geometry, or there's 4 regions of electron density. I keep trying to say these phrases over and over again so you guys get them. Again, based off of the tetrahedral. It's based off of the tetrahedron, but all you see is this bent shape here, okay? And what I want to do is kind of break everything down into the summary of their EDG. So this is the tetrahedral group, or this tetrahedral shape. You can get a trigonal pyramidal molecule or bent from this, okay? Trigonal bipyramidal, again, you have, it all depends on where those electrons go. And as a rule, the electrons go around the equator. So if I ever had, lone pairs is what I'm talking about. So here's the shape, here's the poles, here's the, like, the North Pole and the South Pole. This would be your equator. The electrons, anytime I want to add in a lone pair and substitute out a bonded atom, it goes around the equator. It goes around the equator, okay? So if I put one lone pair here, there's my equator, there's the poles, so it's just on its side. This is called a seesaw shape, okay? Here would be a lone pair. This one's going back behind the board. There's your equator here. So therefore, now I have something called a T-shape. And of course, the third lone pair, I would have one coming down. This is coming out at you. This is going back into the board. There's your equator. There it is, the North and South Pole. It's just on its side. It's tipped on its side. This is called linear. Octahedral group. Again, we have 6 things around the central atom. If I erase one of them, that lone pair would be here. So you don't see it. You don't erase it. You just substitute in a lone pair. And now I have a square pyramid. And here I have something called a square planar right here. Okay? So that's the VSEPR theory. We'll practice several of these. You'll do a bunch in your homework. Okay? If you have questions, let me know.